Hi guys, welcome to module CM42 Energy Resources, or possibly module CM4269 Green and Sustainable Chemistry, as this lecture is shared between the two modules. Okay, today we're going to talk about biofuels, and you should view this lecture as a train journey, and this is the type of route we're going to be taking. I want to look at the basic underlying chemistry of most of the major routes that we might think of to get to biofuels. Towards the end of the lecture, we will look at a bit of technical stuff as well, which is less chemistry and more slightly engineering, I guess. And finally, we'll ask the question, could it happen? Mostly, this lecture is going to be about liquid biofuels. I touch on methane and hydrogen at points, but really it is only touch on. Even for the material I do cover, there's a series of lecture support materials, there's a series of papers. I strongly recommend that you spend some time inside those papers. The chemistry is excellent. Finally, I'm not going to spend a lot of time telling you how you can make biofuel from straw or biofuel from dead frog legs or something. It's underlying process that I'm more interested in. Final thing, implicit in some of these methods is energy. That is, one needs energy to do things. The implicit assumption in those circumstances is that the energy will be from renewable sources, things like solar or wind and such like. And finally, as will sort of become obvious, this is like a treasure chest. There's some wonderful chemistry here, some wonderful solutions. And that's what we do as chemists. We produce tools and solutions in our reactions and mechanisms. But they are not a complete solution. They are a prerequisite to a solution. With it, you need to have economics and you need policy to get a full scope and a full solution. Anyway, okay, let's proceed. So we'll start with a quote. Not all biofuels are the same. That sounds obvious, I guess. But in much of the discussion, you would think that this wasn't the case. You would think that all biofuels are the same to see some of the media coverage. In fact, that's a quote, part of a piece of work by the Parliamentary Commissioner for the Environment. When I was there, we produced this report. Some biofuels are better than others, thinking strategically about biofuels. I'm very proud of that report, and I still agree with myself, which is probably helpful. Totally recommended. There's more there than you'll need. The website is here, and the main report will be in the lecture support materials. There are other reports that support the report work we had done, and that's all available on the PCE website. Okay, so not all biofuels are the same as each other, and we'll now compare one of the differences, which is energy content. So these are approximate numbers because it does depend on the blend, it depends on a few other bits and pieces. But you can see that for petrol, you have an energy of about 33 megajoules per litre. And for the biofuel equivalent, which is ethanol, is 20 megajoules per litre. So there's a big difference here in the amount of energy that you get out of a litre of fuel. And clearly, our fossil fuels, love them or hate them, they are good fuels. They are energy rich. If we look at diesel, which is the other main class of fuel, about 38 megajoules per litre, and you can see the two biodiesel relatives are both contain less energy than the fossil diesel, and kerosene's about 33. Now, some definitions which it's probably worth handling now. If you hear first generation biofuel, what that means is it's biofuel which is obtained directly from food crops. That includes fermenting starch for ethanol, and they're all first generation. And we won't talk too much about it now, but the fact you're using food to make biofuel actually is an issue. Second generation biofuels, some of them can be apparently the same substance, but that's where you're not using food crops to make the biofuel. So wood, waste, things like that. Third generation is effectively more of the same, but more efficiently. So typically you might be able to find something growing which is not a crop, but actually can grow in the desert, land you couldn't otherwise use. That would be third generation. And finally, fourth generation is not only about producing biofuel, it's about capturing or reducing CO2, in fact, carbon negative. So there you go. Looking at this list here, you might think, kerosene. Actually, to give you an example, Air New Zealand now run all of their aircraft on a biofuel. It's actually a Catropha berry. Well, there are a number of types actually. And a number of airlines are now using biofuel for their planes, which I hope is a comforting thought for when you fly. Okay, so not all biofuels are the same. They are different from each other, and they're different from their fossil relatives. So let's go ahead and first of all look, dare I say, at the relatives, at the fossil relatives. And these are just some definitions of the things that we call diesel and petrol, and some of the stuff that we call biodiesel and other things. And you can see in composition and chemistry terms, they are really quite different. So things like diesel, they're a distilled crude fraction between those temperature ranges, typically C8 to 21. Whereas biodiesel is actually the one I've chosen. I could have chosen more, but the older one, I suppose, the original biodiesel, is fatty acid methyl ester. It's C12 to C22. Maybe 90% C16 to C18. And each of these fuels, certainly the fossil fuels, have particular specifications that engineers have built into engines and things like that. And this is important, as we'll find out in a moment. But some of the differences are maybe not obvious. So the sort of ones that maybe are not obvious, and let's take the diesels and biodiesels as examples, but it applies to all, because these are different mixtures that maybe look the same, but maybe their freezing points are different. So if you're using a standard certification of diesel, maybe it freezes at -15, so it's okay, you can use it in the Arctic. Maybe the biodiesel is solid by -5. You can see the type of issues. The densities are different, the viscosities are different. The solubility of water is different. So for petrol, the solubility of water in petrol is very low. But for ethanol, it's miscible with water in all proportions. This throws up issues. And this is one of the reasons one has to be quite careful how you use biofuels, because in the end, you're talking about the engines, and that's where we're going to go now briefly. So, all biofuels are not the same as each other or their fossil counterparts. There are two main messages from this slide. The first is that biofuels, ideally, the sort of biofuel you really want is called a drop-in biofuel. That means you can literally roll up at the factory with your car, lorry, whatever, fill it up at the factory and drive off. Now, there are some types of biofuel that you can do that with, but that's not most of them. Mostly, one actually needs to have a standard blend. And again, this is totally actually due to something called engine guarantees. Last year, we made 60 million new cars in the world. Although the components of cars, different parts, are becoming more expensive, actually, the engine is still one of the major components. And it costs an awful lot of money if a company like Toyota or Renault have to recall, I don't know, the Talbot Horizon years 1989 to 1991 is recalled for a major engine defect. That's the sort of thing that you don't want to be doing if you're a car manufacturer, which means engines are very exhaustively tested and there are specifications for what fuel you can burn in them. If you've got a tanker, an ocean-going oil tanker, you can almost burn old socks in those engines. Diesel engines, not literally obviously, but diesel engines, those big ones, are very robust and they can take very poor quality fuel. If you've got a more modern car though, if you try to put ethanol into it, it'll work, but actually you'll find your fuel lines corrode. You'll find your carburetors begin to rust, a whole bunch of things. So to protect your engine guarantee, effectively there are a number of agreed mixtures of biofuels with fossil fuels at certain specification which allow you to use biofuels. So for trucks, tractors, trains, boats, boilers, you've got the B20 diesel, which is 80% petroleum diesel, 20% biodiesel, or B99 diesel, which is 99% biodiesel and 1% petroleum. And obviously the standard of this biodiesel is much higher than the biodiesel we're talking about here. Each of these have certified specifications. Or for jet aircraft, there's a 50-50 aviation biofuel. So the black again is the petroleum aviation fuel. If we look at other types of blends, so if you have a petrol car, then actually you can buy E10, 10% ethanol, 90% petrol. And there are other specifications here, diesel and biodiesel. Now, there is one important thing we need to just bear in mind. If you think about the way the economy works, diesel is the thing which powers the economy. It's the thing that drives the lorries, that drives the ships, that drives pretty much everything to move goods and services around. Petrol is, if you like, the domestic fuel. It's what we have in our cars. It's not as economically important as diesel. And we'll come back to that later. Okay, I think we've done enough introduction. Let's now get into the lecture. And we'll start with the first of our biofuels, fatty acid methyl ester. Now, this diagram shows you, if you like, traditional fossil fuel diesel, or one of the component molecules of that substance, because it's a mixture, and FAME biodiesel. And you can see, of course, the difference is that one is an alkane and the other is a methyl ester. So the chemistry is old. You will know this from when you started learning chemistry probably. We have triglycerides, which can be fats, vegetable oils. If it's first generation, it'll be one of those. If it's second generation, it'll be waste oil or some other plant oil. And you're reacting that with methanol with a base, usually KOH or NOH. And of course, you remember that methanol will lose a hydrogen to become methoxide, which will then a nucleophilic attack on the carbonyl carbons, and you end up with glycerol. You end up with 3 molecules of effectively your biodiesel, your FAME. Old chemistry, but in terms of biodiesel, probably still the most widely used method to make a biodiesel. And environmentally, if it's not made from food, it's actually reasonably friendly. One of the indicators you might use to look at how environmentally friendly something is how much waste it produces. And effectively, if you look at EF, which is the, let's call it the environmental factor, it's the ratio of the mass of waste divided by the mass of products, and the best value you can get is 0. And because glycerol is a useful product, everything here is product, which means that EF is 0 or very close to 0. A very nice example of a very environmentally friendly process. What we're going to do now is briefly have a look at the stages, if you like, the more engineering part of the journey from triglycerides to nice, clear biodiesel here. And I'm not going to spend time here. You can look at it yourself. First of all, you remove the water vapor and the solids that might be there. Then you remove the glycerol backbone. You add your potassium hydroxide or sodium hydroxide and your methanol, and you add your methanol, and off it goes. These are little diagrams for an automatic system to make biofuel. Okay, let's go on to more interesting chemistry now. What I'd like to do is to go on to the Fischer-Tropsch reaction, which you may well have met, I'm not sure, but the major route before you can use Fischer-Tropsch is to have synthesis gas or syngas. As Mrs. Beaton once said about a recipe for jugged hare, first catch your hare. So let's just remind you, and again, this first part is almost Victorian chemistry. Let's remind you of what syngas is and how you make it. Bear in mind that synthesis gas is the building block for a chemical industry. It used to be, I don't know about Singapore actually, but certainly in the UK and Australia and New Zealand, syngas was piped to houses and called town gas, and people cooked on it. Of course, if you look at the composition of this syngas or town gas, you can see carbon monoxide in here, which is where the expression comes from, put your head in a gas oven. It's one method that people use to commit suicide. And of course, they could die of carbon monoxide poisoning. With modern gas cookers, of course, we use methane, natural gas, and it's not possible to be poisoned because there is no carbon monoxide there. However, it isn't oxygen, so it's not going to do any good. Okay, so we'll first look at the water-gas reaction, which is the reaction you use to make syngas. And there are a couple of variants. You can either react water with carbon at high temperature to get carbon dioxide and hydrogen, or you can react water and methane, burn them together to get carbon dioxide and hydrogen. Now, obviously, these two variants differ in how rich in hydrogen they happen to be. For both these cases where you've used the water-gas reaction, you then need to do a shift reaction to increase the amount of hydrogen. The water-gas reaction is endothermic, which means that you're looking usually at high temperatures to do this reaction. 1200 Kelvin over rain and nickel will usually do the job. And of course, if you're looking at this first variant, you're probably looking at high pressure or highish pressure because you don't have a de Chatelier's issue. But with this second one, you do have a Le Chatelier's issue. You have more moles of product than you do of reactant. Therefore, in those situations, you'd do this reaction at reduced pressure. Okay, so that's the water-gas reaction. Let's now look at the second part of that, which is the shift reaction. And this is somewhat different. This is an equilibrium. So if you're looking at doing this at 500 Kelvin, your Gibbs free energy is minus 20 kilojoules per mole. If you're looking doing it at 1000, it's only 5 kilojoules per mole. Typical conditions to run this second part of the reaction is maybe 700 K with a hematite, so an iron oxide, chromium oxide, magnesium oxide, compound catalysts. Not the same as you'd have in a catalytic converter, but it does have similar chemistries. And then a second stage at slightly cooler at 500 Kelvin with maybe a copper oxide, zinc oxide, and aluminium oxide catalyst. Mechanistically, it's not quite as straightforward as it might seem. Yes, carbon monoxide and water to carbon dioxide and hydrogen, but there are 3 or 4 different routes here. And the only one that I will comment on is this one. Now, this actually has the largest activation energy of any step on this process chart. But I'm not going to go through here. You can see the various mechanisms. And yeah, I don't probably need to walk through it with you now. So that's syngas. We've got our syngas. What we're now going to do is use the Fischer-Tropsch reaction to make biofuels. Now, typically, we would make syngas, so Jurong Island, for instance, will be making syngas, which it will use. And our current chemical industry produces hydrogen, quite a lot of it. If you're talking biofuels, you'll have produced that from biomass or some such. I'm not going to go there and think about all the things you could produce it from, but basically you would pyrolyze biomass. You could even, if you like, make a, in inverted commas, fossil biofuel. If you take very poor quality fossil fuel, let's take lignite, maybe 30% carbon, it's a very low grade coal, almost closer to peat than coal. If you pyrolyze that rather than burn it, which means you heat it under reduced oxygen, you'll get carbon monoxide rather, out of that, and hydrogen. So you could then go on and use the system we're about to talk about now, the Fischer-Tropsch system, to make a biofuel which would have considerably more energy than the original lignite. Equally, from biofuels, you could do the same thing. Anyway, so with that caveat on the source of the carbon you put in, let's think about the reaction. Effectively, what you are doing is you are adding hydrogen to carbon monoxide and getting a hydrocarbon plus water. If we think about the stages of this and the early Fischer-Tropsch, effectively, unless you take quite careful precautions, the hydrocarbon you end up with is methane. The modern catalyst for this is ruthenium nanoparticles, and you'd use it in a fluidized bed reactor. The trick to this reaction, and actually I want you to remember this because later on we're going to be looking at the electrochemical reduction of carbon dioxide, and it's similar. But the trick is you have to have on the surface of the catalyst an opportunity for the carbon atoms to build up in concentration so that then they can react with each other to form the longer chains. What's used now is nano-size particle of ruthenium such that you can have what are called open corners. I'll show you how this works. Nanoparticles are wonderful catalysts because there are quantum effects that make them react in ways which might not be immediately apparent, and certainly not apparent in the bulk material. Anyway, if this technology works, what I hope you're going to see now is this.
This animation shows the fate of carbon atoms on different types of ruthenium nanoparticles. Dihydrogen decomposes rapidly. However, on a dense planar surface, carbon monoxide decomposes slowly into carbon and oxygen. Since there is a low concentration of free carbon atoms, methane and water are the only products. Only on particles that are large enough to support an open corner with coordinatively unsaturated ruthenium atoms can the formation of hydrocarbons occur. On the highly reactive ruthenium atoms in this open corner, carbon monoxide rapidly decomposes and generates enough free carbon to sustain a chain growth mechanism. To allow this process to continue, it is necessary for newly formed carbon-hydrogen moieties to move away from the dissociation site. This mechanism of rapid carbon monoxide dissociation and carbon relocation was discovered in quantum mechanical calculations. This animation shows the fate of carbon atoms on different types of ruthenium nanoparticles. Dihydrogen decomposes rapidly. However, on a dense planar surface, carbon monoxide decomposes slowly into carbon and oxygen. Since there is a low concentration of free carbon atoms, methane and water are the only products. Only on particles that are large enough to support an open corner with coordinatively unsaturated ruthenium atoms can the formation of hydrocarbons occur. On the highly reactive ruthenium atoms in this open corner, carbon monoxide rapidly decomposes and generates enough free carbon to sustain a chain growth mechanism. To allow this process to continue, it is necessary for newly formed carbon-hydrogen moieties to move away from the dissociation site. This mechanism of rapid carbon monoxide dissociation and carbon relocation was discovered in quantum mechanical calculations.
Okay, this gets interesting because you can tailor-make the length of the carbon chain by manipulating the pressure. And in the end, what we need here is nice long chains. We can then do chemistry, more familiar chemistry, to trim them or increase them, to tweak the properties of the compound that we have to make a good fuel. Effectively, this is, as here, it's probably second or third generation. If you could use carbon dioxide from the atmosphere and reduce it to carbon monoxide and then run it through this system, then you're getting into fourth generation, which remember means that actually not only are you making biofuel, you're reducing carbon dioxide, because clearly carbon monoxide is now a good route to organic compounds. And we'll move on into there now. Okay, it's a train journey, and a time check is we're just coming into hydrocarbons from carbon dioxide station. So effectively now we're into fourth generation biofuels. Right, now we're going to take a slight aside. I hate to push the pun too far, but the train's about to go up a siding and a lesser used part track. There are people around who are getting all excited about removing carbon dioxide from the atmosphere and then making biofuel out of it. A good chemist is a lazy chemist. What do I mean by that? I mean a good chemist is an efficient and effective chemist who doesn't waste time doing things which are effectively making difficulty which doesn't have to be there. At the moment, the concentration of carbon dioxide in the atmosphere is about 400 ppm by volume. That's tiny. That carbon dioxide is distributed in the lowest part of the atmosphere, which is the troposphere. The volume of the troposphere, which contains about 80% of the mass of the atmosphere, is about 8 billion cubic kilometers. That's huge. It does not make sense on any planet, including this one, to try to get carbon dioxide out of the atmosphere using chemical plant like this. So, I'm afraid you will find papers in the literature which have that in mind. Bless them. My personal view is that's misguided. However, that doesn't mean to say you can't reduce atmospheric carbon dioxide. It means instead that what you do is you gather your carbon dioxide from emissions that are going into the atmosphere. So typically, if you look at a power station plume, carbon dioxide is usually maybe 3%. Now, if you're doing chemistry, you certainly can't easily, highly efficiently work with 400 ppm carbon dioxide. You can, well, 3% carbon dioxide is actually also not desperately good. But if you use amine scrubbing, which is the way where you can dissolve the carbon dioxide, 3% carbon dioxide in a plume, in an amine solution, the carbon dioxide is trapped, and then when it's reasonably full, you can just move this liquor away, heat it, release the carbon dioxide, and then recycle the amines back again. So this is a carbon dioxide scrubbing system, and it's used typically for carbon capture and storage. But from this, you can produce north of 90% carbon dioxide. That's something, as chemists, we can get our teeth around. We can work with that, and that's fine. So we'll do the thought experiment. If we go this way, then we effectively stop adding carbon dioxide to the atmosphere. Concentrations will stabilize and fall. Yes, there's about a 40 to 50 year time lag, but actually that's no different to any other way, because that's about the dynamics of the atmosphere in the biogeochemical system. So you're not going to get it faster than that anyway. So good chemist is a lazy chemist. Think about these sorts of things before you march off on a save the world mission. This paper, as you probably noticed by now, particular references to particular parts of the lecture are in yellow here. Gives a reasonable overview of CO2 capture from the atmosphere, and they didn't invent this. This technology is at least 30 years old, but they give it, because it's comprehensive, I've given that reference. Okay, so still on the sidetrack, the siding, rather than going straight from carbon dioxide to organic compounds, the siding is going to go, the route's going to go from carbon dioxide to carbon monoxide, and then using Fischer-Tropsch to make your organic compounds. Now, the first way, remember, Fischer-Tropsch is an equilibrium, is to do it chemically, effectively with a reverse water-gas reaction, and then a Fischer-Tropsch in this sort of way. The reference I've given is a thorough review. It's not really satisfactory. The issue is, surprise, surprise, stabilizing intermediates and producing hydrogen without reproducing your carbon dioxide. And it comes down, very similar to the issue with the forward Fischer-Tropsch, where you had to increase the concentrations of intermediates on the surface of the catalyst. There is still quite a problem here. To do the reverse reaction, normally you're looking at rare earth oxide or noble metal catalysts. So this is 2016, that's this year, and this review basically comes to the conclusion, at the moment, there's a lot of problems here. I'm sure they're not insoluble problems, but again, for me, this is a siding. Why go through carbon monoxide if you can go directly? But anyway, let's continue. And we begin to get more interesting now. There are two more sidings, if you will. One is the photochemical reduction of carbon dioxide, photoelectrochemical reduction of carbon dioxide to carbon monoxide. Now, there are a series of problems with electrochemical reduction of carbon dioxide. Effectively, it's not very thermodynamically reversible. It's not very thermodynamically efficient. And in those situations, you have to apply a very high potential, it's called an overpotential, to force the reaction to proceed. You get effectively low current efficiency. The cathode materials are expensive, and the cathode surfaces are usually not very stable. Some progress, yes, but only some progress. Now, in one sense, photoelectrochemical reduction helps some of those problems, but unfortunately gives you other problems. If you illuminate a p-type semiconductor, and gallium arsenide is a good one, effectively it can reduce your potentials at which you can yield electrons. Because what actually happens is that you get electrons coming from the band gap because the conduction band and the particular conduction band actually bends, and valence band as well. You get band bending, which can lower the energy of the electron, and these electrons are coming within the band gap anyway. So, in one sense, that seems like a brilliant idea, and it is a good idea. But there are a slightly different set of problems with this. Now, these reactions are quite kinetically slow. So again, you end up with large overpotentials for a different reason, to get reasonably large currents. And of course, you're competing now with hydrogen. So yes, this is a step forward, but I suspect it's a step forward into a blind alley, or at least at the moment that appears to be the way. However, electrochemical reduction, despite its problems, is something we're going to pursue a bit further. Clearly, it's going to be more efficient to go from carbon dioxide direct to hydrocarbons. And as we just talked, actually the issues are stability of the catalyst, expensive materials, etc., etc. Now, we work in this university, in this department, and you are aware that we are a world-class university, and it gives me very great pleasure to say that one of my colleagues and his group, Dr. Jason Yeo, they are at the forefront of this area, and it's actually their work I'm going to present now. So, well done, Jason and colleagues. I'm actually going to be using some of their slides directly with their permission in this part of the lecture. So these were the problems. Now, Jason's group used agglomerated copper nanocrystals to produce N-propanol directly from CO2. Now, it turns out if you use unagglomerated nanoparticles, you do get hydrocarbons, but you get effectively methane, C1 products. And the results of their work is they seem to have developed a catalyst which seems stable at on a 6-hour timescale, which is significantly better than anything else around. And after 12 hours of continuous use, only 14% deactivation. So again, both of these papers, this paper, the JFIS Chem Let's paper, is actually in the lecture support material. And I'm going to be using slides courtesy of Rendang and Jason from a symposium where these were delivered a week or two ago in the Netherlands. Right, so let's now look at that story in a bit more detail. The situation back in 2010, hydrocarbons going to, carbon dioxide into hydrocarbons. These were the type of substances that we were looking at. Obviously, this type of process, remind us while we're doing it, reduces carbon dioxide emissions. It can produce useful chemicals and fuels. You can use it as an energy storage for renewable energy. And potentially, you can produce a sustainable anthropogenic carbon cycle. So if you're burning fuel to produce carbon dioxide, trapping that carbon dioxide, using sustainable energy to convert that back to hydrocarbons, which you can then burn again, you see suddenly it's a closed loop. That's progress. Okay, so what Jason and his colleagues did was they first looked for a metal catalyst which would give hydrocarbons, preferably not just C1 hydrocarbons, although methane is burnable, you can use it. And again, this is one of their slides. This is some work from 1989, and it shows a series of metals with the types of products that were yielded by carbon dioxide electrochemical reduction. And you can see, although there are some that give very high yields in one or two of these hydrocarbons, there's only one which seems to give hydrocarbons pretty much across the board, and it's therefore relatively easy to see why they chose copper. It seems unique amongst the other metals to give such a range of these hydrocarbons or alcohols. Then they looked at the form of the catalyst that they should use. Now, they went through a series of copper catalysts, annealed, isolated nanoparticles, and I'll let you read that. But I want just to draw your attention to this graph. Actually, this is on annealed, but here you have some classic chemistry. You're looking at the rate of change effectively of carbon monoxide, formic acid on two surfaces, either annealed copper or polycrystalline copper. And you can see here that you get mechanistic information. So on the annealed copper, carbon monoxide is formed first and begins to fall, and at that point then formic acid is formed. So this would allow us to conclude that it's likely that the carbon monoxide being formed here is being used to make the formic acid. The polycrystalline surface is not so plain, but probably a similar story. Now, I'm not going to go through every slide on the whole paper, but I want just to point out the interesting chemistry here. To look at their products, they effectively were using voltammetry, changing the potential and looking at the current response. Now, they identified with, in their work, with more than one of their family of catalysts, extra peaks. You can see them here, you can see them here, and these they attributed to the presence of defects in the copper surface. Now, being kineticists at heart, they immediately plotted surface area against rate of production of propanol, and they found actually no relation. But when they plotted the amount of N-propanol against the defects, suddenly a different story. And this goes back to what we saw on the Fischer-Tropsch catalyst surface. Defects actually stabilize the intermediates on the surface that lead to propanol reaction, or the formation of N-propanol. Effectively, you've got a series of, it's not straightforward, you've got a 2-carbon unit and a 1-carbon unit that have to react, and they have to be on the surface at high enough concentrations for long enough to react. And it's thought that defects stabilize, in fact it's been shown that defects stabilize those intermediates and hence allow this work to happen. So I commend the paper to you. In summary, here are the results. I won't read them. And this is a lovely example of world-class work right, here. And very clever chemistry and very thorough chemistry. And again, I'd like to thank Rendang and Jason Yeo for allowing me to use these slides and to share this. Okay, so I think now what we'll do is we'll congratulate Jason and his colleagues. World-class piece of work, nice one. And we'll end this first half of Biofuels. And thank you, and I'll see you in a minute.